Okay, welcome everyone. We're going to get started tonight. If you come often, let me be the first to tell you I'm not Brian Jackson. If this is your first one, we're happy you're here. If you haven't met me yet, my name is Dr. Rachel Huckmala. I'm not giving the talk, but we got a gaggle of Rachels together for you this evening. I work with Brian Jackson. I am his postdoc. It's a fancy term for I finished my PhD a year ago, and I'm working on pulling off my research training wheels. So that's me. And thank you. Today is our first Friday, so we are here the first Friday of every month, all year, no matter what, rain, snow, sleet, wind, sun. We're in this room, and we also live stream on YouTube, so if rain, snow, sleet is not something you want to be outside in, totally get it, you can watch us on YouTube. Our program here is completely donor supported, so we're able to bring out a new astronomer every month to come and give a lecture to you guys based off of the support that you have for our program. So we thank you for donating, and if you haven't yet, we ask that you consider donating. And now that it is spring, tonight will be our first stargazing after the lecture. So here at the Boise State Quad, which is just that way, big patch of grass, can't miss it. Our students will be out there after the lecture with some telescopes. They said they wanted to look at Jupiter, so we will be looking at Jupiter and whatever else they can find. And we host this every Friday, weather permitting. So we have flyers out on the table. If you haven't grabbed one already, you can grab one on your way out. There is a QR code that you can scan. It will take you to our website that announces stargazing is good or not. We make that announcement by noon every Friday. So make sure that you're checking that. Then Brian also asked me to mention to you guys that there is a lunar eclipse upcoming. It is a full lunar eclipse. The moon will be red. He also wanted me to tell you that we will not be hosting an event because the lunar eclipse is happening at 1 a.m. and that's not a time I would like to be at work. Thank you. So that will be the night of March 13th into the 14th. So, okay. I made a list. I'm sorry. That was all of my points. So now I get to introduce our speaker for tonight. So tonight we have Dr. Rachel Smith that's joining us. Like I said, not me, but her. And Dr. Rachel Smith is the head of astronomy and astrophysics at the North Carolina Museum of Natural Sciences, that's what I said. And she is also a professor at Appalachian State University. And so she will be talking to us tonight about life beyond the solar system. And also she's showcasing for us this very cool program called Open Space, which is a conglomeration of NASA data that you can soar through space with, for lack of a better word. So I'm excited to see it, and I hope that you guys are too. Okay.
All right, thank you. Thanks, everyone. So I'm really happy to be here. I work at a museum, as Rachel said, and I do a lot of outreach, and my favorite kinds of talks are this to people like yourselves who are public, really excited people who want to learn about space. I'm an astrophysicist. I study forming stars, and I'll talk a little bit about my research, but I want to make sure I really cover what I think are the coolest aspects of the search for life. I will tell you that I have these cards about open space. This is free software. It is NASA funded. It is led. This project is we're in our 10th year of working on this software. It is being developed. It's a collaboration with lots of different people, and it's led by the American Museum of Natural History. We're funded partners at North Carolina Museum of Natural Sciences. I have these little cards that I had made up. There's a QR code. You can download the software. I will caution you to check the tech specs that are needed for running open space. It is a gaming. If you're a gamer, this is for you. If you're not a gamer, it's still for you. but just you might need a little time to ramp up, and you might need a computer that can run it. It doesn't like Macs. Sorry. Okay, so I'm probably going to sit and I'm going to show you this software as I take you on a little journey. Whoops, as I fall on my face. Take you on a little journey through. We're going to talk about Earth and the search for life. So, and I'm going to open up some data sets as I do this. And so what you'll see, I have the solar system here. And as you see, I was just having this run as people were coming in. And I'll start off with our solar system. There are 8 planets. Sorry, Pluto. 8 planets. And the solar system is it's a remnant of our protoplanetary disk, which we evolved from 4.5 billion years ago. And you can see the remnants of this disk in the plane of the solar system. And this is showing the planets in that plane. And what I'm going to turn on first in the data set here is I'm going to type it in. I know kind of where I'm going, and there are plenty of data sets you can add into open space. Is I'm going to turn on the habitable zone. Every star has a habitable zone. This is this zone where liquid water, can you all hear me, by the way? Good? Okay. Liquid water can exist on the surface of a planet. And in our solar system, we are the only planet squarely in the habitable zone. And this is our orbit, Earth. And I'm not going to zoom all the way in yet because I'll talk a little bit about our asteroids and comets first. But we have 2 other terrestrial worlds that are too hot and too cold. And that's why sometimes the habitable zone where we are is called the Goldilocks zone, because it's not too hot, it's not too cold, it is just right. But it wasn't always like this. We are, and I'll say this right off the bat, we're the only planet we know of with life. We have not found life anywhere else. And that's remarkable because I'm just showing you a teeny tiny window into space right now. And at the end, we're going to zoom out and see everything in the universe. So it's very hard to wrap our heads around the idea that we're alone. And I'll talk a little bit in this talk. We're going to cover a lot of things, talk about the search for life in the solar system, and talk about SETI, the search for extraterrestrial intelligence. And within that story, I'll tell you a little bit about my own research as well on forming stars and how that feeds into this understanding of are we alone and how do planets like Earth form. But at one point in time, Venus in the inside here was habitable. It was inside the green. And for lots of reasons, it is not habitable now. It is in a runaway greenhouse. It is way too hot. It has a very, very thick atmosphere. Nothing can survive on Venus, we think. And then there's Mars. And you can see, you might say, hey, wait, Mars looks like it's a little bit in the habitable zone. And that's true. And the reason Mars gets an opportunity to stick a toe in the habitable zone is because it's unclear if maybe water can exist for some periods of time on the surface. There's been some evidence that there's been water on the surface for a short period of time coming up from the rocks. And it's very possible that Mars still has water under the rocks. It was absolutely habitable in the past. And we'll go to Mars and I'll show you one of the recent places where we have a rover on Mars. But right now it's just Earth. It's just us. We're the only habitable world. But every exoplanet, every exoplanetary system has a star or multiple stars, and there is a habitable zone. It doesn't mean there's a world in there, but there's a habitable zone. So I'm going to turn off the habitable zone, and I'm just going to talk a little bit. Oops comes up a lot with open space. So I'm going to turn on some of my favorite asteroids. And someone already came up and showed me their meteorite, and I love talking about meteorites. I'm a curator of meteorites. I'm going to turn on a few of my favorite asteroids. Not all of them, but these are our neighbors, guys. These are our friends, especially when they deliver meteorites, but sometimes it's not so fun, and we'll talk a little about that. So these are the only ones I'm turning on, and the reason is for our people streaming, it kind of gets a little crunchy. There's a lot of data. There are millions of asteroids here in the data set, and we see some really cool things. I turned on some comets too. I'll zoom out a little bit. These are our remnants from our protoplanetary disk, from planet formation. We have a lot of stuff in our solar system. We have 8 planets. We've got lots of moons. We have 1 moon, but there are plenty of planets with many moons. And we have an asteroid belt and comets. And these are the remnants from our solar system. So when you see a meteorite and you touch a meteorite, you are touching something that's older than anything on Earth. There aren't any rocks on Earth that date as old as the meteorites because we have plate tectonics and volcanism and all this stuff that mixes up our rocks. And so this is how we learn about our solar system. How did we evolve? How did we what happened in the early solar system? Well, we learned from asteroids and meteorites, and we also learn from stars that are forming today, which is what I study. But a lot of my research relates to meteorites, and I'll talk a little bit about that. Some of my two favorite bunches of asteroids are these two, and these bunny ears here, these rabbit or mouse ears, I should say. These are the Jupiter Trojans, and the reason I show them is it shows how big Jupiter is. It is keeping apart these two giant groups of asteroids, and it's a reminder that Jupiter has kept us free from a lot of impacts. We think when we try to figure out what makes a habitable world, how do we know what's habitable out there? What makes another Earth? One of the things we think, astrobiologists think, is needed is a Jupiter to pull in some of those impacts that could really decimate life. And we have evidence, of course, for asteroid impacts that have done that. But asteroids and meteorites also deliver to our solar system, and we'll talk a little bit about that. So let me I'm going to turn off all of them except for the Mars crossers, and most of the asteroids are between Mars and Jupiter. I'm going to turn them all off except the potentially hazardous and the Mars crossers. And these are the ones that come near us. And before I do that, before I show you a few images, I've overlaid some images with OpenSpace to enhance our discussion. And the first is a protoplanetary disk. This is an artistic rendering of a disk. Our solar system formed, just like other systems are forming today, from a disk of gas and dust around a forming star, in a star-forming cloud, and they're forming today as well. And so I study the gas in the phase before planets to try to understand how these planets formed, and especially looking at carbon and oxygen. And I'll show you some of the data that I've gotten recently. And then I'm going to turn this off. So we're talking a little bit. I wanted to show you the disk, and I'm going to go to some of my bookmarks, and I'm going to pick Meteor Crater, which is one of my favorite craters to start with. So when I start talking about meteorites and asteroids and how that affects life, Meteor Crater is one of the best places to look. Has anyone been there? It's in Arizona near the Grand. Yeah. So it's really well preserved. It's a crater that is not very big by asteroid standards. I'm going to turn off my bubble, and you can bookmark things in OpenSpace. There are all sorts of fun things you can do, and there's tutorials online, by the way. In OpenSpace, as I travel, I'll tell you a little bit about OpenSpace. In OpenSpace, we have some of the best data to look at on Earth, Moon, and Mars. And that's because, first, we're on Earth. We've got all the data. Moon, we've been to the moon. So we have lots of great data for the moon and Mars. And so all the data I show you in OpenSpace is data from the orbiters around those two worlds. For the moon and Mars. So we have Lunar Reconnaissance Orbiter. Even though we're not going to the moon today unless you want me to later after the talk. I teach, so I'm always like, and the moon in the Mars Reconnaissance Orbiter. So all of everything you see in OpenSpace is real data. Everything's data driven. That's a really important part of this project, is to make sure everything is real, data driven, and as best visualizations that can be made to showcase the data. So it's a crater, this crater, which is in Arizona, Winslow, Arizona, near the Grand Canyon, very worth the visit, extremely well preserved. We have about 150 craters on Earth. This is a tiny fraction of the craters that exist on other worlds. And that's because we have a living world, we have dynamics, we have volcanism and geology and weathering and erosion, plate tectonics that erase this history. But this crater stayed because it fell in a desert where there's not a huge amount of erosion. This asteroid fell about 50,000 years ago. And what was there were giant sloths. I like to show what was around, who had, could have been affected. No extinctions for something this small, and woolly mammoths. So this was the Colorado Plateau. It was much more lush back then. And I'll stick around Meteor Crater for a little bit while I talk about asteroids. And I do have a meteorite to show you. It's a little iron, and you can touch it. Irons are pretty robust. They fell through space. I like to tell people, the meteorites you have fell through space. So they're pretty robust, but some are more fragile than others. Irons are really interesting, being the core of a failed planet. But where else do we get impacts? There's some pretty well-known places. One in particular, this happened in Russia in 2013. This is the Chelyabinsk impact. This was captured on dash cams in Chelyabinsk in Siberia. We do have samples of this at the museum, and I'll show you a sample that I was able to get in Chelyabinsk. I went over there for a meeting. We went to this city, and someone brought over all the meteorites they found, and we bought them. And it was captured. People didn't know what it was. They thought they were under attack. It was thousands of tons of TNT. This is much more energy than a single bomb. And the reason we don't feel that impact is because it explodes in the atmosphere. But space can deliver way more than we could ever generate. So the delivery of molecules for life, of water, could have easily happened from space billions of years ago. And we don't know exactly how Earth got its oceans and how Earth got the molecules for life. And so studying meteorites and impacts is a window into understanding this. This is showing a map of the Yucatan, and in particular, the asteroid that killed what? The dinosaurs. So this is Chicxulub. It's underwater, and this is the Yucatan Peninsula. This is well known to be the cause of the extinction. I mean, we don't know 100%, but it's pretty close to 100 for lots of lines of evidence that the 65 million years ago, this impact happened in the Yucatan and led to the final demise of the dinosaurs. And because of that, the trajectory of mammals could happen, and here we are. And so the evolution of life on Earth is really affected by extinction events. And this is a very famous one that everybody remembers. We have dramatic sketches of it. I don't like the ones where the poor dinosaurs are like crying to the sky, because I love animals. But this was okay. I thought I still like reptiles, but I had to pick something. This is Chelyabinsk. This is I will say, when you if a meteorite is seen to fall, they're very fresh, and you see that beautiful fusion crust, and they're picked up right away if people see them fall, and then you get a really pristine meteorite. And so this is a specimen that I bought in Chelyabinsk. It's at the museum, and it's a beautiful representation of that fusion crust. It's just an ordinary chondrite. That's the classification. But because it was seen to fall, and the only documented injuries from an asteroid impact in history, it's very famous. This is a meteorite that has amino acids. This is Tarda in our collection. It fell in 2020 in Morocco, and this is ours, and it has some very interesting aspects. I won't get too far into it because we have a lot to cover today, but it has amino acids, and amino acids are complex molecules. Some are organic that all life needs, and amino acids survive in meteorites. It doesn't mean there's life in there, but it means the molecules needed for life, some of them at least, survive in meteorites. And that's, again, this kind of understanding how did life start? Could the molecules needed for life be delivered from space? It's quite possible, because they are protected inside these meteorites. And so some meteorites have amino acids, and they're particularly interesting. These are comets, right? We get comets coming to Earth. This is a picture I took outside our front yard in North Carolina, in Cedar Grove, where I live. And that's Comet Neowise. And sometimes we get really nice comets coming. Comets are from farther away. They're from beyond the orbit of Neptune. So asteroids are much closer. Comets are big balls of ice. Again, pristine remnants from our early solar system. And we have there's some missions going to comets. We have sample return from a comet. All this really cool science trying to understand comets. And so again, we get this delivery coming from space all the time. If you're worried, don't worry too much about getting hit, because this is a plot that shows a very clear relationship between size and timing between impacts. So essentially, the bigger the impactor, the less likely it's going to happen. And you can see that the KT meteor, which did in the dinosaurs, every 100 million years. And as scientists we think in orders of magnitude. So 65 is the same as 100. So a lot of people say, well, we're due for another. It's actually not technically true in the next 100 years, because we can map out these trajectories out to 100 years. So in the next 100 years, don't worry, nothing's happening. Chelyabinsk happens, a meteor that size happens every 10 or so years. So we're getting this influx of material, and every day we get tons of tiny pieces. Most of it falls in the water, because we're 75% covered with water, but we will get hit again. And a planet destroyer hopefully won't happen, but who knows, we may not even be here to see it. So that's my discussion of meteorites and impacts. And I will show you this last thing. This is Chelyabinsk. This is what happened when it hit. And the reason there's glass there, well, certainly the meteor came, the light, people saw the light first because light travels faster than sound. They stuck their faces up to the windows. What is that? And then boom, the shock wave came and people got glass in their faces. So nobody died and there weren't severe injuries, but this was the injury. Mostly was glass hitting people's faces. Okay, so now we're going to move on. I hate to say we got a limited time. I would love to talk to you all night, but we're going to go on to Mars. Everybody loves Mars, right? So we're going to go to Mars. And with open space, let me make sure we're going to Jezero. We're going to fly to Jezero faster than the speed of light, which we can never do. Keep in mind, we're not going anywhere. I hate to say it. I don't like to disappoint people, but we are not going anywhere pretty fast. Like, so we travel at 0.0005% the speed of light with a rocket. We need to go way faster to get anywhere. And so Mars is our next stop with humans, probably after the moon, but it'll still take a long time. So when we're thinking about extraterrestrial life and you're thinking about being visited by UFOs, keep in mind that kind of travel is really hard. And we're very young in doing our travel too. We don't know what's possible because we are extremely young in our technology. And I'll talk a little bit about SETI. I have to turn on the Mars layers, which I didn't do. So let me do that. With open space, there are lots of cool layers you can turn on in data sets. And I like to teach my students a little bit about data sets and visualization when we turn it. Oh, I should just do it this way. Let's see, global and Mars and turn on. And then I'm going to turn off high rise. And there we go. Okay, so Jezero crater. I see it here. We are at Jezero now with with Perseverance, the rover Perseverance. I'm going to turn off my little bubble because I found it. The little bubbles help me because things are small. Space is big, little things are small. But Mars, we don't have time. We could do a whole talk on Mars. But Mars had water in the past. It is evident. You can see this here with Jezero. You can see here that this was an ancient river delta, and we know this from spectroscopy too, that there's organics and there's microbiolites and all this geology that says that there was water on Mars. And this was an ancient delta. So you see the river flowed here, fanned out into this crater. This is an impact crater. And I'll zoom down. So Mars 2020 or Perseverance landed right about here. And they got that landing really close. It was amazing what these engineers at the Jet Propulsion Lab can do. And I'll zip around here and we'll zoom down. And we'll talk a little bit about Mars. Am I on Mars? Yes. I meant the focus point. So I'm not telling you exactly how to use all of this, but there is a way to drive where you have to be focused on the planet you're on. So otherwise we'll go all over the place. And if I'm making you dizzy, I also drive my car this way. So sorry, it is how I drive. So this is, you can see all these cool features. What Jezero is doing, what Perseverance is doing is going around this crater and looking for evidence of water, evidence of past life, if there is any, and there isn't so far, and also doing something called geocaching, where the rover is taking vials and shoving in material to hold on to stay there for a possible Mars sample return. Now, as you may have heard in the news, that's very expensive, and they just fired a whole bunch of people at JPL to do that mission, so who knows when that's ever going to happen, but the intention is there, and the goal is to eventually get to Mars. I want to turn on my height layer. There we go. So you can turn on all these layers and then see the height and this is all real data. This is data from the Mars Reconnaissance Orbiter that we're seeing in open space. These are wind features here. And if you're a geologist or you're interested in geology, there's all sorts of geology that you can look at in open space. So there was water in the past in this crater. And where there's water, there's maybe life. That's what is this notion of the habitable zone, and astrobiology is all life on Earth needs water and all life on Earth is carbon-based. Is that true for all life in the universe? Well, we don't know, but we have to start with what we know. And what we know is every single life form on Earth needs liquid water and is based in carbon. And so what happened? What is the past and future of Mars? Well, we have some evidence on Earth that can help us decide, what could have happened. I'll pause for that. I just want to mention one more thing about Perseverance, and that is this little helicopter, Ingenuity. This is my favorite part of this mission. this little helicopter is a tiny drone. It is the first powered flight on another world. And this is amazing. The engineers decided at the last minute to stick this thing on to see if they could fly in the very thin atmosphere of, 100 times thinner than Earth, and fly this drone. And it flew 72 flights. About the highest was 80 feet, which is really, it sounds like not a lot, but it is. It flew a total of about 2 hours, a little over 2 hours. And of all these there's really nice imagery of it. There it is flying up there. And then it damaged its rotor. And if there's any kind of anthropomorphization that affects you, it's the sadness that people said the poor little thing died. It's a little machine, but it was sad. It made me sad, I have to tell you. But in the past, there was water, and these are stromatolites. These are ancient microbial mats in Australia. And this is the kind of biology that could have existed in Mars's past. And there's some evidence from the Mars Reconnaissance Orbiter that this type of geology exists on Mars. Not the life necessarily, but evidence for past microbial mats maybe. But again, no evidence for life yet, but trying to figure out what the water world on Mars could have been. But remember, life started on Earth probably within the first billion years of Earth's existence. And at that point, Mars was losing its atmosphere, lost its magnetic field, and is now subject to the solar wind stripping off its atmosphere. So that means if we want to send humans to Mars, we could not breathe on Mars. We'd have to be in spacesuits and in a habitat. So this is a conception of a habitat. This is my favorite one because I like blue and it looks cool, but nobody knows what it's going to look like. This is from NASA, actually. And this is what it might look, something to generate maybe greenhouse gases. How can we're good at that, right? But we can't control it so well. How can we terraform Mars? Could we ever? Nobody knows. But we can't live there permanently. This is not our next home right now. So we have to take care of Earth. But maybe, I like this next one, maybe one day this could be us. All right, so let's move on. We got places to go. All right, so let's go. We're going to go next through the solar system. We're going to go to Europa because Europa is really important. Europa is a moon of Jupiter, and you can see the nest of moons around Jupiter. All these big planets have like about 100 moons or so, maybe 95. And Europa is the next best place for astrobiology, even more interesting than Mars, I'll say, because it has a global ocean. We know pretty certainly that it does. And we know this from this striping here. This is brine or salty water coming up through the cracks in the ice. And I left the asteroids on so you can feel stressed. Oh, no. But no, and so we're sending Europa Clipper there. So Europa Clipper is launched. You may have heard about it. And it's going to do flybys of Jupiter. It'll get to Jupiter in about 2030. And it will study the ocean from remote sensing. It's not going to land on Europa because we don't have a way to do that. And we don't have a way to not contaminate that ocean. And it's very expensive to get a lander and dig through that ice. So we're not doing that, unfortunately. We as in the collective humanity, but we are going to learn more about this ocean. Europa is smaller than our moon, but if it has this global ocean that we think is kept warm by the pull of Jupiter, it has more water than on Earth. And could there be life in there? Maybe, because we think life probably started under the ocean in a hydrothermal vent type of system, which could exist on Europa because of the pull of Jupiter. And all that nice hot water and pulling and rock could be great for chemistry. So it's really exciting for astrobiology. I kind of think it's farther away, but I'm also really excited about Titan. And there is a mission that's been scheduled to go to Titan, and it's called Dragonfly. And I really like, now Titan is a moon of Saturn. And we know Saturn very well because of its beautiful rings. And you can see it's got a moon. I'm going to fly. You can see Saturn's rings here. All of this imagery from the Cassini mission is really amazing, but we're going to stop. We just did a little quick hello to Saturn and going to talk a second about Titan. Titan is very interesting for two reasons. Well, two reasons. One, it has these hydrocarbon lakes. So it is the only other body in the solar system, any moon or planet except for Earth, that is liquid on the surface, but it is not liquid water. It is liquid hydrocarbon, like ethanol, methane, ethanol, formaldehyde, all those hydrocarbons, which is still exciting for astrobiology because it's liquid and it's carbon, but it's very cold. So one reason life does not exist flourish in these hydrocarbon lakes is because this is like negative 400 degrees and metabolism would be very slow. So we really don't think that this is habitable with life that we understand, but scientists have open minds enough to really explore this world, because this is really an interesting world. Landed on Titan before with the Huygens probe, part of the Cassini mission in the early 2000s, and now hopefully going back with Dragonfly. The second reason it's interesting is it has a really thick nitrogen atmosphere, so which is like the primordial Earth, we think, the early Earth. So it's really interesting to study for the early Earth. This is a concept of Dragonfly, which would be the next, 2.0 of Ingenuity, that little drone on Mars. So that helicopter on Mars helped pave the way for something like Dragonfly, which looks even bigger and better, right? The like next phase of Terminator 2. That's Dragonfly. So we really want to explore these worlds. Will we find life on them? Maybe not, but it's still really important to understand the context of Earth. How do we fit in the solar system with all these possible places beyond the habitable zone that could maybe have had life, maybe have some life? And if we find evidence of any life that's not from Earth, then we can say we are not alone. And that's pretty substantial. That's a big thing to say and think about. And we'll talk more about that with SETI. But before I do that, what I'm going to do is take a quick moment, and I'll run through this a little bit quickly because I want to talk more about SETI. But I'm going to take you back to Earth, to Mauna Kea. Hello, Mauna Kea. Let's go. And that is where I do my observation. So I study forming stars. And so I'm not looking for life, but I'm looking at the chemistry that would lead to life. And Mauna Kea is in the Big Island of Hawaii. And I use the infrared telescope facility on Mauna Kea. So I'm going to turn this off. And one thing I do on Mauna Kea, one thing about this telescope that's really great, besides the fact that it's got an excellent spectrometer, is that you can go to the summit to observe. And I emphasize this because it's part of being a scientist to connect with the natural world, whatever you're studying. And as an astronomer, we don't have a lot of opportunity to do that. And the only opportunity we get to do that is when we can go to our telescopes. And I've done this in a couple of different ways. I flew on SOFIA when it was going, which is an airborne observatory. But now we have this ground-based observatory. And we have 13. There are 13 observatories on Mauna Kea. And this is one of the only ones that still lets astronomers go up there. This is the one right here. It's at 14,000 feet. And you can see these beautiful cinder cones, by the way. This is all the way it looks. It's an amazing place to go. If you've ever been to Hawaii, the Big Island is spectacular, and Mauna Kea is amazing. And they let you up there, and as long as you have shown, but after one time, that you don't fall over and you can survive the night, they will let you stay and do it again. And so I've been up there many times, and I'll show you a couple images of that. So this is the way it looks. I took this picture when I was up there a couple years ago, my last observing run, and I'm submitting for something else coming up, but this is the way it looks. It's a 3-meter telescope. So it's not that big compared to other telescopes. This is me in the dome. Being inside the dome, it's hard to describe how cool it is to be inside this instrument, be on a mountaintop where it's you and a couple other people, isolated from everything else, all distractions from the rest of the world. And you're also part of this mission of people who, most of the people on the mountain are not astronomers. What they are telescope operators, engineers, cooks, people who work in the little lodge you stay in. And you're part of, for a moment, you're part of their team. And it's really spectacular. Not only that, it's an amazing piece of engineering. It was built in the 1970s to support Voyager, which I'll talk about in a minute. This is cooling down the instrument. So the instrument is called ISHO, and this is shown here in the red box. It's infrared astronomy, so you have to keep it cold. So it's use liquid nitrogen to keep it cold. And every night when they do it, they cool down the instruments and get it ready. Oh, and I'll just say, since I don't have a lot of pictures to show you, we observe through this window in this room next to it. We open the dome and we observe. This is what the room looks like. So the telescope operator sits here, I sit here, and I run the instrument, and he goes to the stars that I tell him we want us to go to. And that's me. High elevation, your brain, it still works, but that's a guider image of one of the stars. So you can see the hot dust around this forming star. They're massive stars that we can see at the 3-meter telescope. And I'm looking at studying the CO, the carbon monoxide, in the gas around the star. These are the spectra. And these are the fingerprints of CO. So these are some of the best spectra out there in the infrared, near infrared for these massive stars. Each box is another star. And these lines are CO. And I analyze these lines and get abundance measurements and gas temperatures, and I'm able to compare the data to meteorites and get some answers. This is what it looks like when you take an image before they get to the spectral form, which you reduce later with codes. You get these images, and this is showing the binary. And I show this one because you see the tracks, the top track and this bottom track. That's the binary. This is two stars forming together. So this is my favorite target because it's two stars forming together, and they're beautiful CO lines. And I just love it because you can compare these stars. And this is showing both stars. So this is showing the black one is one of them, binary, and the green is another one. And these are just different transitions of the CO, really deep, nice lines. You get really excited if you're a spectroscopist. This is some great stuff. And then lastly, you guys know this guy, right? Luke Skywalker. Well, this was science fiction in the 1970s, and it's not anymore. Those two suns are known to be the most common architecture in the galaxy. Binary suns were thought to be a fanciful, imaginary science fiction universe by George Lucas, and it's not anymore. Sometimes, occasionally, we catch up to that science fiction and we say, hey, look, we now know this is true. And it wasn't because of Star Wars. It's just because we learn more. And now we have two suns, and you know, it's Tatooine, but we haven't discovered that. But we have two suns, and it's the most common. Most stars out there form in binary systems. So we're helping to, our work on binaries helps create a understanding of many, many types of systems that we're trying to learn. Now, this guy, Carl Sagan, I'm going to transition a little bit. I will say he was in charge of the Voyager mission, or one of the people. I remember I said IRTF, the NASA IRTF, was built to support the Voyager mission, which was there to take pictures of the giant planets. But that wasn't all it did. He also, this was the mission, a little probe. We have two probes. They're the farthest we've ever sent any object out to space. Been going 1 million miles per day since the 1970s, and it's still not past the solar system. Still has to go through the Oort cloud of comets way out there. So we, again, fastest we ever gone, still not past our own solar system. So keep that in mind. Pale blue dot, right? That was Voyager. There's Earth, that little white dot. That was very famous. And if you should listen, Google pale blue dot and listen to the few minutes of Carl Sagan talking about what this means to him. And it really put in perspective. This is a tiny pixel, which is Earth, in a sunbeam of light. And he said, we need to turn this instrument around and look at Earth. He was a poet and a scientist. And he really got people thinking about astronomy, the public. He paved the way for all of us to talk to people about astronomy. He's one of my favorite people to really inspiring person. Pale blue dot really got people thinking about environmentalism and thinking about how could it be we're alone? Everything on Earth is in that tiny pixel. And what does that make you think about as citizens of Earth? That's up to everyone to decide. And on this mission are Voyager, these two records. And these are the golden records. And they're on each probe. And they're sights and sounds of Earth. And you can Google the golden records. You can download the sights and sounds of Earth, of what they put on there. Chuck Berry and languages. And it's a time capsule from the 1970s. And the reason it's on there, these are instructions for aliens. So people say, aliens, if they're out there, that's silly or stuff. Carl Sagan put that on there. He inspired SETI, the Search for Extraterrestrial Intelligence. And we're going to talk about that in a second. And directions, where we are, we're here. He thought it was so important that even if we're not going to be here to see this, to know extraterrestrials, they should know we were here. That's important. We don't always get that feedback we want, but they should know, because everyone should know, all life should know that they're not alone. And that is part of the legacy of Sagan and Voyager. And I just like that connection with the telescope, even though my work doesn't include Voyager. So UFOs. Okay, so you're all here probably to hear about this. So let me, I'm going to turn on the exoplanets. And we have data sets of exoplanets in open space. And there's a slight, let me put my glasses on. Hold on. Exoplanet. So we have, what I'm going to do now is I'm going to turn on a couple of things. I'm turning on the exoplanets, and I'm going to turn on the radiosphere. So the radiosphere is a sphere. It's an imaginary, it's a theoretical sphere, but it's the distance we've sent signals out to space. and it is 100 light years in every direction. And so that means that for 100 years, we've been sending signals out first through radio, then through TV, and now we're kind of growing dark, right? Because we're not really using those signals anymore. So that's a question to think about for SETI, and I'm trying to zoom out a little faster. So Earth is in the center of this radiosphere, and here we go. I'm going to turn off the asteroids as well because they're probably slowing me down a tiny bit. So hold on. Mars, you go. All right. So let's think a little beyond our solar system. Actually, let me focus on the sun. That might make it a little better. All right. So, and for some reason labels are on, but that's all right. I didn't mean to turn those on. But now, exoplanets, every circle and dot is an exoplanetary system that's been discovered. And some are candidates, they're called, but they'll probably be verified as systems. And here you can see this is our radiosphere. So we're in the galaxy. Every star you see in the sky is in our galaxy. And this is our sphere of exoplanets. So there are many, we have many neighbors, and we have not heard a single peep from anybody. So SETI is listening. We want to go to these exoplanets. Now, we can't even get beyond our own solar system. So are we going to go to any of these? Not in any time soon, unfortunately, but we can inventory them and study them. So I'm going to zoom out some more. And this is we have an image of our galaxy. We can't get a full data picture of our galaxy. Our galaxy is 100 light years across, 100,000 light years across. So from this end to this end would take 100,000 years for light to travel, which is much faster than we could ever travel. Speed of light, 100,000 years end to end. This is, keep in mind, these are the exoplanets we've discovered. We still think every star should have a planet, but we just haven't seen them yet because we're technologically not able to. But our radiosphere is a tiny dot inside those exoplanets in that data set. So that's as far as our signals have gone so far. So if there's an alien civilization, say 75,000 light years away, they've got a long time to wait for any signal to come from us. And we have a very long time to wait for any signal to come from them. So when you think about aliens and UFOs and visitors, such as I was going to show you here in science fiction and are inspired, so many of you are here maybe to say, hey, UFOs, when the Earth stood still, Close Encounters, if you're not familiar, I have a whole talk I give on UFOs. We are in our culture, Hollywood has ingrained in us this idea that UFOs are out there, that UFOs are aliens, and they are out there and they visited us. But I bring this up because I don't think that's possible, given the distances of space. Most of space is empty space. And anyway, we've just in our own galaxy, so let's keep going. Each dot is a galaxy here in open space. And we're going to keep going. Each galaxy has hundreds of billions of stars. Our galaxy has about 200 billion, 400 billion. Each galaxy, each dot has hundreds of billions of stars. This is also what inspires the search for life. How could we be alone? It's very hard to believe that. I actually don't believe it. I think we're probably not alone. But the thought of ever, unfortunately, reaching these beings, whatever they are, is very remote and impossible to, unfortunately, comprehend. And we're going to go out. We have clusters of galaxies. This is the Planck data set. We have some blind spots there because we can't see everything. And then finally, the farthest we can see is the cosmic microwave background. This is the remnant. I'll zoom in a second. This is the remnant of the Big Bang. The heat left over from 13.8 billion years ago from our Big Bang. This is as far as we can see in our universe. We have not heard from anybody remotely close to us or even far away from us. And we don't even know what's beyond. So with open space, we just get a sphere. We don't know what the universe is expanding into, and it is expanding and it is accelerating. We don't know if that'll continue. We have no definition for that black stuff because the laws of physics and time started at the Big Bang. So there's so many fundamental mysteries. And yet we approach scientifically, what could it be? And I'll just zoom back in a little bit so you can see some of these galaxies. And I'll finish up by talking a little bit more about SETI. I just have a couple more things. So let's sit around. We'll sit out here in this universe where we can't even go. And we have ideas of aliens. And it is impossible, on thinking about space and time, to think that they visited us. And it was Carl Sagan and Frank Drake that came up with this equation called the Sagan-Drake equation. And I'll just spend a second talking about it. it's a pretty simple equation, and it starts with N, and N is the number of intelligent civilizations defined as communicating off their planet, so not like dolphins or things, communicating off their planet with a telescope in the galaxy. So how do you wrap your head around any number when we don't have that answer and we're the only ones with life that we know of? Well, there are several factors you can think about, and the first is R, which is star formation rate. We have a pretty good idea of what that number is. R is known. FP, what fractions of stars have planets? Well, we really think that every star should have at least one planet. So that number is now well known. And then we know these better than even when Drake and Sagan were making up this equation. Sagan died in 1996, so it's been a long time. What fraction of these planets, NE, are Earth-like, meaning terrestrial, rocky, with potential, could support life? What fraction of these planets have life? We don't know that. As we get down this line, we know little less and less. What fraction we can conjecture? Take maybe 1 out of 8 because we have 1 out of 8. Who knows? You can come up with theoretical models for this. What fraction of the planets with life is intelligent life? Again, getting into philosophy here, we don't really know that much about how we can put a number there, but we can go down the line and then say fraction with civilizations. And then finally, L. And this is the most interesting one to me because this is longevity. How long do these civilizations last? And if you know about technology, and since the invention of the radio, we've invented nuclear technology, and all of the technology needed to get us to space also is used in destructive ways and making bombs and our climate and all of this stuff that could annihilate us before we even get to anywhere. So L could be rather low. And there are a lot of scientists who think about this as well. But these are all the factors needed to calculate the number of intelligent civilizations. And it's an objective way to try to get at some number. But if N is 10,000, which is a pretty conservative number, the closest civilization, if spread evenly throughout the galaxy, would be 900 light years away, which means it would take 900 years for light to travel from that one to our closest neighbor and back. So if that's true, if there is a civilization out there, we would not have heard from them by now, and they wouldn't have heard from us. And traveling through space is very difficult. And so this is kind of a way to think about how can we know how many civilizations are out there. And keep in mind that everything is very far apart. And Carl Sagan famously said, space is vast and the stars are far apart. He was a believer. We don't use that word a lot in science, but he was a believer in SETI. And he wanted to do SETI. He thought it was so worthwhile and wrote the book Contact, which is an excellent film as well. You should see it if you haven't, about communicating with extraterrestrials. And I think that makes him rather unique and important to remember that just because we don't have the answer doesn't mean we shouldn't think about these big questions. And this is my second to last slide. This is how do you think about these civilizations? And this one way to think about them is Kardashev was a Russian physicist, and he came up with three categories: type 1, 2, and 3. Type 1, and based on the way they use energy. Type 1 is using your planet. Do you efficiently use your planet? And we don't even do that yet, right? We're not efficient about it. We don't really harness and sustainably use our planet. So we're thought of as type 0 or maybe between 0 and 1. Humans could reach type 1 in a few hundred years, it's thought. Type 2 is famous. If you're interested in SETI, you may have heard of a Dyson sphere. And that's a type of sphere that a civilization could wrap around their star to harness the energy of their star. And we could observe the infrared heat, that's the waste heat off of that contraption that they might make. And there are studies to look at. There's an astronomer at UCLA who wrote a paper recently. His name is Ben Zuckerman, on how you might know you observed a Dyson sphere. And he's not even a believer. He even says that there are no extraterrestrials near us. So I asked him once about this. I said, hey, you don't even think they're there. What are you doing? What business do you have? No. And he said, well, now you at least know if you saw it, you have a number. You can use my paper. So that's good. And then so I think he believes somewhat a little bit. So type 3 is Star Wars, galactic. You're zipping around, speed of light. And so the reason I bring this up for SETI is, what are we looking for? What kind of life do you think could be out there? I don't think the little green men are the type of life. I think it's going to be very advanced. And statistically, it would be much more advanced than us because the universe is very old compared to our solar system. And we are very young. Is that it could be in another dimension. It could be something we just have no idea what we would look for. And there's lots of thoughts on this about looking for maybe not even biological life. And so this is another way to think about advanced life. Nevertheless, this is what you think about with aliens, right? Is Roswell, this cutie coming to your room and abducting you and all this stuff? There's plenty of stories about this, a lot of conspiracy theories about it. People insist they see aliens, and I know about it, and it's fascinating, the historical, cultural aspect of extraterrestrials. And all I'll say is that, well, this is unlikely and has no scientific evidence for it because everything has to be rigorously studied to be validated. And there was absolutely none of that for sightings, no matter where it is, Roswell or Area 51 or anywhere. It is still part of the discourse. And that keeps us going as scientists, it keeps us exploring, and is also arguably more interesting to think about as a story. And that's what we do as humans. We tell stories to ourselves and to others when we don't fully understand the whole picture, and that's okay to do. And that keeps us creative and thinking of new ways to explore. So that's what I'll say about that. So I have a talk on UFOs that I do. I've done at the museum, and I really like talking about it because it weaves in this culture and science fiction to the actual science. And that is a really important part of all of our work. So that is pretty much what I'll say. And I'll say too, if you want to learn more about open space, you can download this yourself. I have cards. You can take them. They're free. We just made them. This is a NASA-funded project. We want people to use the software to explore, and have a little iron meteorite that you can come and look at. I just ask you can pick it up to see how heavy it is. It is the core of a failed planet. This one is called Campo de Cielo. It was found in the 1500s by monks. It's a pretty cool story about this in Argentina. They're pretty robust. Just don't walk around with it. Don't drop it, even though I know it fell through space, like I'm aware. It's the core of a failed planet. We can't sample our own core, but we can sample meteoritic iron. Pure iron came to Earth from meteorites, and we have pieces of that through meteorites. So I would love to take your questions. And yes, first question. Oh, not in this one. Yeah. Yeah, that's a great question. So the question is, how do the amino acids basically become in the meteorites and then get to Earth? So all of the stuff we need for life and chemistry, all of the molecules for planets are out there. Everything. And the chemistry happens in the interstellar medium and in star forming clouds on ice grains and silicate grains. And all of that chemistry can happen in space and happen on Earth as well. So you don't need a fully formed planet for amino acids to form. So all that chemistry happened. We observe multi-carbon molecules out in space. All of the organic molecules are out there. And so in space, it's a failed planet like a planetesimal or some asteroid, that chemistry happened. And those molecules were preserved in those more rocky meteorites, not the irons, but a rocky meteorite preserved in them because that chemistry is happening everywhere. And that's what's exciting about seeing those molecules, is that we know it's happening. We know they survive impact, and yet we just don't have the whole story together. But it absolutely is not unique to Earth to have any of this chemistry going on. Yeah.
So how common is it that, or how possible is it that you might find one of these laying around somewhere?
Yeah, how common? Yeah, good questions. How common is it to find meteorites? Very rare, very rare. And so I get people coming and asking me if they have a meteorite. It's always no, except the one person who did have a meteorite because he found it in a dresser drawer and he didn't find it in his driveway. It is very rare, especially since you often don't see them fall and they've been sitting around for thousands of years. The expeditions that do find a lot of them are in the deserts of Northwest Africa, and they're in Antarctica, although NSF just got cut, unfortunately, those Antarctic missions, which is sad. Maybe they'll come back. But finding those meteorites in deserts where they are preserved. So it's very uncommon to actually find a meteorite. The most common finds that are meteorites are irons because they look so weird, but they're the least likely to fall. So you're most likely to get a rocky meteorite falling, but they're least likely to be picked up because they look like regular rocks. So a lot of people bring in irons, and it's usually smelted iron from a foundry. We have iron on Earth from smelting and work in factories with iron ores and stuff like that. So Common misconceptions about people thinking they have meteorites is that they have a metallic Earth rock, but it is pretty rare. Yeah.
I'm just wondering, what is your personal idea about what aliens may look like?
Yeah, what's my personal idea of what aliens look like? Wow, I almost wish it was looking like that guy with the big eyes. I don't know. I didn't show you any of the scary ones because sometimes I think the scary ones are funnier, more interesting. I got to tell you, we don't know, but I will say this: when you see aliens and you see something even that looks like this is all still made with our idea of ourselves. We use our, and there's a whole history of these they're called gray aliens, a whole history of that, and really it's everything we imagine comes out of our own heads and what we think is the weirdest version of ourselves. And so it's unusual to see interpretations of aliens that are very different from that, and some movies do that. There are some about languages and weird ethereal things, but this is really our perception, and I think we have no idea at all what they could possibly look like. But it's such a good question. But that's why we see stuff with eyes and arms and legs. Yeah. Yeah. Would it be possible we wouldn't even know? I think that's more likely, but not watching us. I don't believe in the zoo hypothesis that aliens are here watching us, looking at us, because to become an extraterrestrial that explores, you are naturally curious. You build a telescope, you build a spaceship, you're curious about what's out there. So if you find a planet with life and it's obvious that there's no life right around us, you're going to explore it. And I don't think it makes any sense logically that aliens would come and hover around and not make their presence known. I do think it's possible that if we ever discover aliens or they find us, they will likely not be in a form like this. And so that's what I think. They could be in some kind of dimension or something, but it's unlikely that they're going to look like this. I feel like I shouldn't leave this slide up. People are going to be like, whoa, yeah.
In the world that you live in,
Oh, yeah.
which also, how do you guys frame up those incidents of unexplained
Yeah.
phenomena that we now have record?
Yeah. So how do we explain UFOs? Well, anything you see, if you can't explain it, it has to go through the rigorous scientific process of what is it. And so the UFOs, like from the Navy, for example, the drones of New Jersey, I'm more skeptical. I think that was even less interesting. But the naval observations are interesting, and there's a whole list of things those could be, from the pilots thinking they saw something, or equipment, or mirages, or drones, or whatever. Everything has, no matter what the ideas are, everything has to be ruled out before we say it's extraterrestrial. The proof has to be pristine, and it has to go through rigorous scientific process of multiple observations and peer review and all the things we do as scientists to get things published. So even if we don't have an explanation, I personally think it's probably some military thing or illusion or something. I don't know, but just because I don't know doesn't mean it's extraterrestrial. And I also think, given how hard it is to get through space and what I do understand about interstellar travel, it's very unlikely to be a flying saucer or something made of sticks or tinfoil like that landed in Roswell, which led to that big conspiracy saying the government's covering up aliens. The stuff they found was from balloons, but they said it's sticks and tape and paper. There's absolutely no way aliens are going to travel with sticks and paper and glue through space, So yeah, I think it just has to go through the rigor. And there's a lot of stuff out there with theories of what certain things could be, whether it's UFOs or pyramids or all these different ideas. But you have to remember, anecdotal is not evidence. It has to go through, an evidence-based process. And so that's the unfortunate answer, which I know is not that satisfactory. There's a question? No? Someone was getting dressed. Oh, yeah. Oh, so the question is, would they be worried? So about from Star Trek, would they be worried about the Prime Directive? Would they be worried about bothering us because ethically it would be wrong to interfere? Well, we don't have that problem on Earth, so I think that life is not going to do that. I don't know. They'd probably be better than us. I think we have to. There's something called the Great Filter, which is an idea that is human. There's something that for SETI where they think all intelligent life, it's thought of, has to pass through a great filter, which is some filter, and it's not certain what that is, where after that you can really expand and become a starfaring and spacefaring civilization. It could be climate change, it could be some kind of disaster, it could be something we either already passed through or we're going to pass through. And so I think that advanced civilizations may have better ethics and morality maybe than we will with the way we treat life on Earth, because I don't think we would do that. I think we are going to go to Mars and we're going to go to other planets, whether there's life on there or not. I do think that right now, the way we are, we probably will do that. Would future life do that? I don't know, but there's no evidence for anything watching us. And I still think that life is curious. And if they're advanced enough, they'd find a way to come to us and interact some way. I love that. I always think of the Twilight Zone when I think of this. Yeah.
What's the current status of SETI?
What's the current status of SETI? Well, it's holding on. It's still there as an institute. And SETI is cheap. This radio astronomy is really cheap to do. Radio dishes are not even nearly expensive as optical infrared, which is what we use on Mauna Kea. It's cheap to do and listen. So if people can get funding to support themselves to do it, they do it. And it's about supporting yourself really to do it, because there are arrays around in California. You don't even need dark skies. And unfortunately, our Arecibo fell apart. So there's radio dishes. Green Bank is one of them in Virginia. So the status has always been teetering, but it's still there. It's still going. Yeah.
If life exists like on some other planetary body in our solar system, what do you think is like the most likely?
So the most likely life we'll find in our solar system is in our solar system.
Yeah.
Oh, what planetary body? If we could find life, I think Europa is the most likely. It'll be microbial life. We're not going to find anything that cool, I think, like fish even. And most of life on Earth was microbial for the many billions of years until the Cambrian explosion, until photosynthesis and stuff. So for the most of the existence of life on Earth, it was microbial. It's the easiest to hold on and survive extreme conditions. So I think any life we find will be in an extreme condition beyond the habitable zone, will be microbial if we find it. Give back. Yeah.
How often do amino acids fall with
Oh, how often do amino acids fall with carbonaceous carbon? Not that many. There's a handful. It's a small fraction of meteorites that have amino acids, but they're like, maybe 100 or so. It's a decent amount, and you don't need a huge amount of meteorites to study it. It's not a lot though. Yeah.
In your work, you said before
Yeah.
you say one of the questions that you're excited about.
Yeah, I'm excited about what am I excited about in my own research? I'm excited about the oxygen. And I did a science colloquium earlier today, and I didn't have time to talk about that today. But in the spectra I was showing you, that's CO, and within the CO, there's oxygen. And I'm looking at the isotopes of oxygen to see, and I'm seeing this pattern in the isotopes that compares to meteorites, and that tells us about the early solar system. And so I'm very excited about those spectra, and I'm getting that paper out. So if my collaborators listening, I'm doing it. I'm getting the paper out. I'm a little slow with that, but I'm doing it. But yeah, looking at what I'm particularly excited about is we're finding, since you asked, results that support that the cloud, the big molecular cloud that seeds all of these systems, is responsible for a lot of the chemistry. So there's like an inheritance from the cloud to the disk. And that means that there could be many more habitable worlds from a single cloud. So that's the basic conclusion. But when the paper comes out, please read it too, because I just ruined it. But yeah, that's what I'm excited about. Yeah. You have to speak a teeny bit louder for me. Oh, is the existence information of life limited to 3 dimensions? So you're thinking of time or some other? Well, if I didn't say it, I'll say it now. I think it's quite possible that life could exist in other dimensions, because other dimensions are possible based on string theory. There's a possibility of a multiverse. We may never know that because it's not testable right now. So certainly possible. A lot of this stuff, as scientists, we say it's possible because we just don't know. It doesn't mean it's probable, but it's possible. And I think you have to remember there are billions of years of evolution before we even came on the scene. And we've only been around for a few million years. So, I mean, as humans, and 100 years as advanced technology. So what's out there could be so advanced that we can't even know what we're looking for yet. So yeah, I think it's certainly possible. Yeah.
You said binary stars are pretty common.
Yeah.
They're out there.
Yeah.
So, like, how close are they? And then do the planets do like a
No, yeah.
between them, or do they go around both?
Yeah, so binary stars. Binary stars, it depends on the system, how close they are. We're talking, so we think in AU with distances. So 1 AU is between the Earth and the Sun. So the Monarch 2 system could be a few hundred AU between the stars. So they're very big. These disks can be very big. We don't know certainly exactly for all the stars, but it could be tens to hundreds of AU apart, as long as they're gravitationally bound. And it would depend on the size of the star, what dictates that. And then you asked about the planets. No, a figure 8 would not be sustainable, but it would the planets are either orbiting one star or both stars. It just depends on how close they are. So if they're close enough that the planet can orbit, then that's possible. And that has been observed. Usually with exoplanets, they observe the planets orbiting one of the stars of a multiple system, because that's just more stable. And then you can get into the question of habitability. Nobody knows how habitable it would be to be close to a neighboring star. So that's a whole big question of astrobiology. It's a good question.
Okay, I think we'll.
Oh, I'll stay for your questions if you want. Yeah, but
Yes.
you can close
We
out
will
if you
thank our
want.
speaker, and
Thank you.
this is our day.
Thank you. Thanks.
Dr. Rachel Smith will stay up here to answer
Yeah.
more questions. You don't want to ask me your questions about this. I have bad answers. And we will be out on the quad with the telescopes if you're interested in doing some stargazing tonight. So, thank
Okay.
you all for being here.
And we can turn the
Hopefully
lights
we'll see you
on,
next
too.
month.
And I'll turn this off. Should I?
Yes.
All right.
Oh, no, stop.
Thanks. Turn this off. Thank you.
Loved your enthusiasm.
Thank you.
And the humor.
Oh, thank you.
Thank you so
Nice. Thank you for coming. This is yes, you can. You can just stick around here with it, just because I have it. It's very
May I?
heavy. Yes,
Yeah.
please. Everyone can take.
Thank you.
These are great. Of course. Thanks for coming. Thanks for all the great questions. It's heavy for its size. That's.
Oh, you got one. All right.
Oh, is that? I don't know. Yeah, there you go.
Here you go.
I'll probably get one of my